So Brownian motion was first described in 60 BC. So this was described by Titus Lucretius, who was a Greek philosopher, and the way he described it was as the motion of dust particles in a sunbeam entering a dark room. So when you see a sunlight entering a dark room, you can see dust particles dancing in it, and that is a random walk, and that is what is Brownian motion. So this Brownian motion is named after Robert Brown. So Robert Brown was a botanist, and in 1827 he observed pollen grains following a random walk on the water. And then it is also called a Wiener process because Wiener put it on firm mathematical foundations. So let us describe its mathematical properties. So at time t, say your particle is here, and then you add to it some random variable. The random variable you add to it comes from the normal distribution with mean 0 and variance 1. So you add to it some random variable. So this random variable, say, takes this particle here. So at time t your particle is here, at time t plus 1 it is here. So you have added a random distance. So the change in distance wt plus 1 minus w2 is nothing but a random variable comes from the distribution normal with mean 0 and variance 1. Now rather than doing plus 1 every time, you say that okay, you are at time s, and what is the position at time t plus s? Now obviously the position is random, you can never tell where the exact position will be, but you can say that this difference would always be a normal distribution with mean 0 and variance t. So what does this mean? So say at time s, here you are at time s. So where would you be at time t plus s? So after time t plus s, that is time t has elapsed, where would you be? So what you do is you draw a random variable from the normal distribution with mean 0 and variance t and add it to the position here. So say you found the first time you do a sampling, you find some place here. So this distance you have found from the normal distribution with mean 0 and variance t. So notice that whatever happened before s has no bearing on the next time elapsed t. So this is independent of the past. So what we are concerned about, this t is the time elapse. So from s you have gone to t plus s. So the time difference is t. So the next motion only happens based on the time difference t. It has nothing to do with the past. The second property is that at 0 it is at position 0. And third is it is continuous and nowhere differentiable. So this third fact is mathematically deep, and we are not going to touch it, but this is important. So E2 calculus is based on this. Now we have already talked about random walk, and that is also a kind of Brownian motion, and we have shown how it is simulated in lectures on time series. So here we are going to do simulation again, but we are going to take the perspective of stochastic differential equations. So rather than thinking about time series, we are going to think in terms of stochastic differential equations, and soon the difference would become apparent. So let us talk about an example now. So say you consider a stock price at time t as x of t, and this follows a law. So at time t plus 1, the stock price is dependent upon what it was at time t plus some random shock, and this random shock comes from this normal distribution with mean 0 and variance 1. Now you can rewrite this difference xt plus 1 minus xt. You're taking xt on this side, so this you write as dxt. So xt plus 1 minus xt, this is equal to epsilon t. So this is equal to this epsilon t, but this epsilon t is normally distributed with mean 0 and variance 1. So instead of epsilon t, which is a random variable drawn from normal 0 1, you write this random variable wt plus 1 minus wt. So that is what we have written here, and this you can write as dwt. So we get our first stochastic differential equation. So what we have now is a stochastic differential equation. dx of t is equal to dwt. So this is the stochastic part. So this you call the stochastic part of the differential equation. Now notice that we have taken the time difference delta t as 1. So you're going from t to t plus 1. Now that is the perspective we had in time series. We were always going from t to t plus 1. But in stochastic differential equations, you could make this delta t as small as possible. So notice that when you go from s to s plus t, this t could be greater than 1 or this t could be less than 1. This t could be anything. So this t could be as well as 0.01. So 0.01. This t could be really small, and that is the beauty of stochastic differential equations, that you could make time as small as possible. And we are going to talk about this later on. So what does the stochastic differential equation say? So this stochastic differential equation simply says that the stoch xt follows Brownian motion. Now for simulation, we are going to use this UEMA package. This is developed by academicians at Tokyo University. So that is the beauty of R, is that it beats all other software because thousands of people are working on it and making these amazing packages. So you can install this package via this command. You don't have to type it. It is given in the description of the video. So copy paste it and run this once. So you run this command once. So you're going to install package this UEMA from this repository. So now we are going to simulate this model. So these are the set of commands. So require UEMA is clear. You have to run this command so that R knows where to get its model from. So M1 is the name of the model. You could set your own name. We are going to set model. Drift is 0. So we're going to talk about drift later on. So there is no drift in this model. Diffusion is 1. So 1 is multiple of this. So this equation you can write as 1 times dWt. So this 1 comes here. So this is a diffusion. State variable is x. So this is a state variable, and you're going to solve for this variable x2. And time variable is t. So we are taking as initial stock price is 100. X I NIT is 100. So you can put your own stock price here. We are just writing as 100 here. So this is just simulate command. It will simulate it. Then we will plot x. And then this d1 is from x, we are just going to take data out. So if you just type in x and hit enter, then you're going to get a lot of things. This x is a big object in UEMA, so it has a lot of small things in it. So we are just concerned with the data part of it, what is generated, and that's why we are taking original data out. So you just type in x and run it also to see what comes out, and then we are going to run d1. So before I move further, let us again talk about this delta t being really small. So as I said, the delta t is really small. For simulation purpose, our package is going to make a grid. So this is how the grid is going to look like. So the grid is from 0 to 1, and we are going to do 100 simulations in it. So there are 100 simulations. So every delta t is nothing but 1 by 100. So this is the delta t we are going to use. Now you can change this delta t, change this grid. When we run this thing on R, I will change the grid and make the grid to 1 by 1000, and then we will have 1000 simulations. So we will see that when we run this set of commands. So let us run these commands. I have already installed the package, so I'm not going to run this, but we will run the rest of the commands. So let us do it. So you require the package UEMA. You have set the model. Drift is 0, diffusion is 1, state variable is x, time variable is t. So let us just run these commands here. Hit the run button. So this it gives you a warning that delta is redefined. So it has redefined our delta. Let us just plot it right now. So once you plot it, you get some path. Starts at 100, goes up and down like this. So every time you simulate it and plot it, it will give you different Brownian motion. So you get a different graph. Now let us run again. You will get a different graph. So you see, starting from 100, now you ended up here. So every time you run it, you get a different graph. So simulation once is useless. So you have to simulate it 1000 times and make a probability distribution out of it to understand where this Brownian motion is leading you to. So let us make the grid again to 1000. So now you will do 1000 sample 1000 points in the grid. So your terminal is 1, that is you're going to go from this point to this point as just 1, and now in this graph there are 100 points. Now you are going to have 1000 points here. So let us see this. Let's run this, and now you can see the graph has become more choppy because you have added 1000 points instead of 100. So let us keep running this, and you can see that every time you run it you will get a different graph. Every time you run it you will get a different graph. So it is important that we make a corresponding probability distribution to it, and that we will do in the next lecture.